Well, hello, IB Juniors. So sorry to have not been here today. Unfortunately, my son was sent home sick today, so I was in daddy mode and I had to stay home to make sure that he was healthy. Not to mention the school said he couldn't come back for 24 hours. Anyway, howdy nerds. So today you are going to start Unit 15, boom, integration, which is literally the inverse operation of finding a derivative. What is the purpose of integration, you might ask? Well, essentially, integration is used to find the area under a curve. That's a kind of a lame definition, but for now it'll work. Now, we can estimate the area under a curve several ways. Now, in our curriculum, we're only going to learn about two, but there are many, many more ways to estimate it. And we'll get exact answers later on in the unit. So one method to divide the area is to, is to divide the area into several rectangles. And those rectangles all have to have an equal width. So however far apart you decide to make your first x and your next x, every rectangle has to be exactly the same width. Now, what we can do is we can either say that the right hand of each rectangle is a y value on our curve, or we could say the left-hand corner of the top of the rectangle is on our curve. So we would call this upper rectangles because pieces of it are above the curve. And we would call this lower rectangles because, well, the entire rectangle is below the curve. Now, I'm hoping you can see that this area of these rectangles, if we were to add up the areas of these rectangles, would be okay, hold on. Let's start over again. The idea is cut it up into rectangles and find the area of the rectangles. There we go. Anyway, because each of these rectangles has a, let's call it a triangular piece above the curve, I'm hoping that you'll see that upper rectangle's answer will always be a little bit bigger than what the actual area is. And by the same token, this curve has triangular, let's call them pieces, below it that sit on top of the rectangles that does not get accounted for. So no matter what you do, the lower rectangle estimate for area will always be a little bit less than the real thing. Now, wouldn't it be great if the actual area was the average of these two? Yeah, it's not. Sorry, it's just not. And it is the way it is. So we're going to practice it. I've never seen an IB question like it, but it is a good skill to have. When in doubt, you could always use it if you were super pinched to just make, say, an estimate. Now, if you want that estimate to be better, you know what you could do? Make more rectangles. Make them skinnier. Because if you were to make these rectangles skinnier and skinnier and skinnier, this piece of area above the curve or this piece of area below the curve would get smaller and smaller and smaller. So technically, if you could cut this into an infinite number of rectangles, you'd have the exact answer because each one of these triangular things would approach the size of 0. So we're going to consider the function x squared plus 1. This is a parabola. Vertex is on the y-axis at 0, 1. We're going to estimate the area that is enclosed by this curve, the x-axis, and two vertical lines, x equals 1 and x equals 4. We've been told to divide our area into 3 strips. So we want 3 rectangles, and each of those 3 rectangles needs to be of equal length. I'm going to say equal width. I don't know, equal length. I don't like that verbiage. I would say that this is the width. Anyway, we're going to do it once with upper rectangles, once with lower rectangles. So I'm going to draw 2 different pictures. Now, picture not drawn to scale, but I am going to do my best. And let's see. We're going to x equals 4, right? So x equals 1, x equals 4. So I need 1, 2, 3 marks in here. There, I did my best. Whoa, I can't count. Kind of in a pickle here, aren't I? Well, I'm not going to reprint these and start over, so we'll just have to do our best. We'll say 4 is there now. This one is a figment of your imagination. And let's say y equals 1 is right here where our vertex sits. And what are we going to do? We're going to plug in x equals 1 into this right here and get 1 squared plus 1, which is 2. Here's 2. And I'm a little bit frightened by this one because look what happens when we plug in 4. 16 plus 1, 17. Yikes. Picture ridiculously not drawn to scale, but we're going to do our best, okay? We're going to say it was like there-ish. And then we're going to draw our curve. There it is. For this one, we wanted upper rectangle, so we want it to look like this one, where the top right-hand corner of the rectangle sits on the curve. There's one. There's two. And we'll pretend that 4 wasn't drunk and landed right there. There's 3. I mean, I think you can, we'll say it's right there. I don't know. I goofed up with the black pen and I can't fix it now. Sue me. So what do we need to do in order to find the area of these rectangles? Well, it's just length times width, and they all have the same width. 1, 1, 1. How about that? So really what we need to do is we need to know how tall are each of these rectangles. Well, since the right-hand corner is on the y-axis, on the curve, the y value is going to come from just plugging that number in for y. So this first rectangle, if we plug 2 in, we're going to get this value, which happens to be this height. 2 squared is 4 plus 1 is 5. There we go. This rectangle, if we plug in 3, it's going to give us this y value. 3 squared plus 1 is 9 plus 1, which is 10. And this one we already know, 4 squared plus 1 is 17. So this area is 1 times 5 plus 1 times 10 plus 1 times 17. Again, the 1s are because each of these rectangles has a width of 1. This being in green are confusing. Let's do that. The next picture will be much better, I promise. So that is 15 plus 17, an area of 32. Now, let us estimate the exact same area, but we're going to use lower rectangles this time. And I'm kind of got in my way on the right-hand side here, so I'm going to have to draw this picture down here. This will be for part B with my right-hand rectangles. One, 2, 3, 4. I'm not going to try to get cutesy with it this time. I'm just going to draw them all out. And we already know the vertex sits at 1, 1. And we know the maximum value is at 4, 17 because it's the exact same equation. Yeah. Okay. When we plug in x equals 1, we know that's going to give us y equals 2 because 1 squared plus 1 is 2. And we already know that 4 squared plus 1 is 17. Gets like this, and it does something like this. Okay? These rectangles now are going to be below the curve, which means their top left corner is the one that sits on the curve. Like that. Once again, these rectangles all have a width of 1. But now we need to figure out how tall they are. Well, this height is right here. It's actually going to come from when x is 1. So when x is 1, we plug it in to get this y value. We can see that it's a 2. This middle rectangle, its height is coming from this point right here when x was 2. When we plug in x is 2, we get 2 squared, which is 4, plus 1, which is 5. And then lastly, this rectangle uses x equals 3 for its height. 3 squared is 9 plus 1 is 10. So the lower area estimation would be 1 times 2 plus 1 times 5 plus 1 times 10, giving us 17. Wow, that is actually a really big difference. And in a couple lessons, we'll be able to figure out what the exact area is when I teach you how to actually do integrals. Now, the other way that we can estimate areas underneath curves is by using known shapes. So we've got some fanciness going on here. And I already kind of alluded to this earlier, but we allow the width of those strips of the rectangles to approach 0. This would allow our error to go to 0. Doing that is actually called the definite integral. And this is the symbol for integral. When we read this, the integral from a to b, that means, from a to b on this shape, of fx dx. I don't want you to get too bent out of shape right now on the symbol and the dx. Just know that this and this are together as one thing. almost as if you wanted to treat the function as the argument of the operation integral. So this and this go together, they are one symbol. If every y value of your equation is at or above the x-axis, meaning all of our y values are positive or 0, no negative y values, for every single x, then the area is literally under the curve above the x-axis. So one more time, as long as every one of your y values is above the x-axis, then the shaded area under the curve, is calculated by doing the definite integral. Again, we don't know how to do that just yet. But what we do know how to do is use shapes to find areas, like we just used rectangles. Here we're going to use some graphical evidence and known area facts to figure out what the definite integral from 0 to 2, what the integral from 0 to 2 of 2x plus 1 dx is. This, ladies and gentlemen, is a straight line. Its y-intercept is 1, its slope is 2. We're only going from x equals 0 to x equals 2, so 1, 2. And we know at x equals 0, I get 0 plus 1, which is 1. And at x equals 2, I get 2 times 2, which is 4. 4 plus 1 is 5. And we have been tasked with finding the area underneath this line. I don't know about you, but I'm seeing a right triangle. And I know how to find the area of a triangle. It's just 1/2 base times height. Well, I could see the base. It's 2. And I could see the height. It's 5. Two times 5 is 10, and half of that is 5. So the area underneath that curve, technically all things are known as curves, is 5. Pretty darn easy, right? Right, Mr. M? Fantastic. I'm glad you agree. Now this second one. I doubt there's very many people in the room or in the YouTube video right now that know what this graph looks like. Tell you what, let's just say you didn't have a choice. Let's say you had y equals square root of 1 minus x squared. And you're like, you know what? I've never really seen an x squared graph underneath a square root bar. I'm a little confused about what that would look like. And I go, fine. Why don't we square it just to see what happens? And I'm going to add x squared to both sides. Well, golly gee, that is the equation for the unit circle. You know, a circle, x squared plus y squared, centered at 0, 0, with a radius of 1. But it took me to square both sides to get that. So what is that? Well, let's do this in reverse order. Let's get y by itself. Subtract x squared from both sides. Take the square root of both sides. And now check this out. You have to remember that every time you cancel a square with a square root, it creates a plus or a minus. I didn't have plus or minus. I only had the plus version. So what does that mean? That means that this is the positive half of this circle. The positive half of this circle. That means the half of this circle that is above the x-axis. If you didn't understand all of that, don't worry about it. I just need you to be able to find the area of a circle. We said it was centered at 0, 0 with a radius of 1. Here is the graph, that we're dealing with. Now, I have been asked to find the area of the half circle because I've only been asked to go from x equals 0 to x equals 1. So I don't have half of a circle. No, what I actually have is a quarter of a circle. So area of a circle is pi r squared, but I only have 1/4 of that. So our area would be 1/4 pi r squared. So the integral from 0 to 1 of the square root of 1 minus x squared dx can actually be calculated by doing 1/4 times pi times my radius squared, which is pi over 4. Boom, baby. And that is the entire first lesson. I hope it's easy peasy and it's not too confusing. You're literally finding the area of rectangles, adding it up, areas of known shapes. It's that easy. And of course, if you have any questions, I will be here on Monday. You can ask away. Have a nice weekend. Be safe, be smart. You know who I'm talking to.